Thanks for joining this session on quantum computing. My name is Nadia Carlston. I lead product at the AWS Center for Quantum Computing, and I will be joined later today by Fernando Brandao, who leads quantum algorithms. Today, we'll talk about building a fault-tolerant quantum computer. And by the end of the session, you'll understand why it's such an important goal for anyone interested in advanced computation. And you'll also get a first peek at what our quantum hardware looks like. First, I will introduce the Center for Quantum Computing, who we are and what we do. I'll then talk about why quantum computers might be useful and some of the challenges in building them in a way that they can deliver on that potential. We'll introduce the concept of quantum error correction, which is necessary to get accurate computation at larger scales. And Fernando will dive deep into how AWS is implementing this into hardware we are building. And finally, we'll talk about scaling, how we go from quantum devices we can make today to devices we need for practical applications. The AWS Center for Quantum Computing is dedicated to innovating on quantum technologies for the long term. This is where we design, build, and test quantum devices. We're located in California and just opened a brand new facility. If you look at the picture, we're the tan building at the front. The main purpose of this facility is to do research and development. So in addition to office space, we also have state-of-the-art labs and specialized equipment here. We are located on the Caltech campus. This makes it a very nice place to work, but it also means that we can interact with researchers and students on campus. We believe it's important to stay connected to basic research, and having this environment where we can collaborate between industry and academia is especially helpful. The center is also a nice example of how AWS is thinking big when it comes to a long-term vision for quantum. We are taking on some pretty big goals and executing on a large-scale engineering effort, as you'll see. One of our main goals is to move towards scalable, high-fidelity quantum computers. Computers that have both accuracy of computation and size necessary to try to solve meaningful problems. It's a very hard thing to do, but fortunately, we've assembled a great team to work on all of the challenges ahead of us. We're taking an integrated approach to these problems. We have quantum hardware and quantum algorithms teams, and they are working side by side to tackle many topics related to quantum development. On the theory side, a big area of focus for us is quantum error correction. We're also working on application areas and designing better quantum algorithms. One example is simulations of quantum systems and applications to many-body physics. How we can use quantum computers to understand how systems of particles behave and interact. On the hardware side of things, we spend a lot of time thinking about design, layout, and fabrication of quantum processors. How we can improve architectures, for example, or increase the fab yield. It also takes a lot of supporting technologies to make a good quantum computer, including cryogenics and systems to control its various parts. Software development is also critical. Having a good software stack helps us automate things like calibration, which down the line will mean more reliable machines for our customers. We have a great team, but we're not doing it all alone. We have ongoing collaborations with several universities to do research in some of these areas. We also have an awesome group of Amazon scholars that are working with us and contributing their expertise to this effort. So now that you know a bit about who we are and what we do, let's talk about why we're so excited about quantum. Quantum computing is about taking advantage of quantum mechanics, which is the set of physical laws that apply at micro and nanoscales to do computation in a new way. Why is that important? One, it's a completely different paradigm of computing. It's not about taking classical processors and making them faster. a quantum computer is fundamentally different in how it works. Because we're using these properties of quantum mechanics, we're able to store and process information in completely new ways. I'll go over that in more detail in a couple slides. But the takeaway here is that this makes it possible to have a completely different trajectory of performance improvement. It turns out that there are certain types of problems that are so hard that there's no way to solve them efficiently on classical computers, even supercomputers. And when I say solve efficiently, I'm talking about the computational resources needed to solve the problem, like the number of steps or how much memory we need. What's crucial is how that scales with the size of the problem. In everyday life, we're pretty familiar with linear scaling, the blue line on the chart. In the world of scientific computation, we're mostly concerned about exponential scaling, the red line, versus polynomial scaling, the purple line. This set of problems, where resources needed grow exponentially with input size, is really problematic for classical computing. And a big reason for the current interest in quantum computers is that some of these problems can be solved in polynomial time on a quantum computer. Whereas even using the best classical approach for the same problem would require exponential time. So let's take a look at some of these areas. The first thing I want to note is that not all algorithms can be sped up by running them on a quantum computer. Only certain ones are known to show a quantum advantage. But we know that there are some problems where quantum approaches do have promise. And these problems are ones that can be impactful for many application areas and for customers in many different industries. One area where quantum is already having an impact is how we think about cryptography and encryption. Shor's algorithm was the first that addressed an important practical problem, the factorization of large numbers. The fact that it's so difficult to factor large numbers is why it's the basis for encryption. But now that we know this can be done more efficiently on quantum computers, there's a lot of interest in alternative forms of encryption. Another application is simulating quantum systems. Simulating nature is very difficult for classical systems, and there's reason to believe that these computations scale better on quantum computers. And if we do this better, it also helps us model new molecules and predict their properties better. So we also expect that quantum computers will eventually play a big role in accelerating discovery of new materials. Another area of interest for customers is optimization, like adjusting portfolios and financial services or routing for logistics companies. There are classical approximations that can be used to get a good enough answer, but being able to improve these solutions with quantum potentially means significantly reducing costs. So clearly there's a lot of potential for quantum, but there's a catch. Solving any meaningful problems in any of these areas requires many qubits. And as we'll see, these qubits also have to be very reliable. One of the things that makes quantum computers different is how information is stored. A classical bit is binary. It's in either of two logical states, 0 or 1. If you take a transistor and the switch is off, there's no voltage applied, so the logic state will be 0. If you then turn that switch on, that will represent your state 1. And at any moment in time, you can be certain which state your system is in. The fundamental elements of quantum computers are qubits. They're also binary in the sense that they can be initialized in state 0 or state 1, but we now have this unique quantum property called superposition, which means that a single quantum state can carry aspects of both state 0 and state 1. So how does superposition help us? It means that a qubit can carry a lot more information compared to classical bits. For a number n bits, there are 2 to the n possible classical states. A classical computer can only represent one of these states at a time. If you want to process more than that, then you basically have two options. You can give it more time and do it sequentially, or you can do it in parallel by putting more hardware on the problem. In contrast, with quantum computers, we benefit from the fact that a single state of superposition can carry aspects of all 2 to the n possible states. This is why those complex problems that we talked about scale so much better on quantum computers. If we look at how quantum computers do gate operations, there are similarities with classical computers. Classical computing is performed using a universal set of gates to implement logic. There are single-bit gates like the NOT gate, which inverts input logic, but to do computation, single-bit gates are not enough. We need some form of logical operation that acts on multiple qubits. So we use things like the AND gate, where you only get an output of 1 if both inputs are 1, otherwise you get a 0. Similarly, quantum computation happens by performing logic gates on qubits. So we have quantum equivalents of classical gates. They work by taking a quantum state as the input, and there will be a qubit rotation to get to the correct state. There's also gates that act on multiple qubits. So for example, here in the middle of the circuit, we have a CNOT gate, which is the quantum equivalent of an exclusive OR gate. It takes two inputs, and the rotation of one qubit will depend on the state of the other qubit. So the way we perform gates is different, but the idea is the same. We can design a subset of single and two qubit gates that becomes a universal gate set. And with this, we can perform any quantum algorithm on a gate model quantum computer. There isn't a single way to build a quantum computer because there are many ways to physically realize a qubit. And as a quantum community, we haven't converged on one way that is the best on all fronts. So we're still at the stage where different research groups and different companies are pursuing different approaches. And there are now different types of NISQ devices also becoming available. NISQ stands for Noisy Intermediate Scale Quantum Devices, and they are so called because they're still small in number of qubits and limited by noise in what they can do. Some NISQ devices are based on trapped ions. Here you can use electrically charged atoms as the qubit, and you trap them using oscillating fields above a microfabricated trap, which you can see here. So you can manipulate them using laser beams. One of the advantages is these qubits are very stable, but the trade-off is that gate operations are very slow. It's also possible to use neutral atoms as the qubits. And you can also trap them and manipulate their interactions. These Rydberg atoms are typically used to emulate quantum systems. Another option is photonic devices, where quantum information is processed using optical components like beam splitters and phase shifters. And you get a result by counting photons at the end of the computation. Another approach that is popular is using superconducting qubits. This is actually what we have chosen to focus our hardware development efforts at AWS. So let's dive a little bit deeper. Superconducting qubits are manufactured, unlike atoms or ions, which are found in nature. They are electrical circuits that behave like atoms. So let's take a super simple circuit. We have an inductor in parallel with a capacitor. Charge in this circuit will oscillate between these two elements. It either sits on the capacitor, or it will move through the inductor and then return to the capacitor to recharge it. So this circuit is an example of an electrical oscillator. But to make a superconducting qubit, we need the oscillator to be nonlinear. So we have to modify the inductor a bit. The reason for that is if I take a harmonic oscillator, its quantum energy levels will be evenly spaced. That's a problem for using it as a qubit, because if I want to drive the qubit from the 0 state to state 1, I can't do this reliably because energy for this transition is the same as the energy to excite other transitions. So we need to somehow make this oscillator anharmonic so that the energy levels are no longer equally spaced. We can do this by introducing a nonlinear inductor into the LC circuit, and it's a very special component called a Josephson junction. You can see a picture here of one taken with a scanning electron microscope. Superconducting qubits have several advantages, one of them being that they leverage microfabrication techniques from the semiconductor industry. So we can fab large numbers of qubits on a silicon wafer. Another advantage is that they have very fast quantum gates compared to other types of qubits. And finally, simple resonator circuits can be great building blocks for experimenting with more complex architectures as we scale. Now I'd like to show you what a superconducting quantum computer actually looks like, since it's not something that most people get to see every day. So first we have a chip that has some qubits patterned on it. The design of it can vary quite a bit. We can experiment with different materials and with different layouts. And the actual processor is actually pretty small, just a few centimeters. But for it to work, there's a lot of additional components that we need. The chip is enclosed in a package that's made out of metal. This is to shield it from external sources of noise. It also provides a way to have communication channels between the chip and the rest of the system. One of the biggest downsides of superconducting qubits is that they require very low temperatures to operate. So the processor is inside a dilution refrigerator, which has different temperature stages that reach progressively lower temperatures, all the way down to about 10 millikelvins. You'll also notice there's a lot of wiring inside. It's designed to optimize heat load. This is important because the device is at the coldest temperature, but it needs to communicate with electronics that are at room temperature. These fridges are very big. The middle image gives you a sense of scale for what it looks like. It takes up a good part of the room. And outside the dilution fridge, there's additional racks of electronics that control the processor. Now, in this picture, one of our engineers is working on a fridge that's open, but while the processor is being used, the system is generally closed, and there are multiple layers of shielding to protect the quantum computer from noise. Noise is the enemy of quantum, and a lot of what we do when we're building quantum systems is trying to figure out how to best protect quantum information from noise. So what's noise? Noise is really any interactions between our qubit and the environment. It can be a result of electromagnetic noise, radiation, magnetic fields, and some of these interactions cause qubit performance to degrade. Over time, what will happen is the qubit interacts more and more with the environment, and the noise will alter the qubit state until information is lost. One metric we can use to quantify how robust the qubit is how long we can maintain the qubit state. We call this coherence time. For classical computers, we don't really need to worry about error rates. Things like bit flips do happen, but they are very rare. For quantum systems, even a tiny amount of noise completely ruins the computation. That's because each gate operation has a probability of adding an error. And since we need to perform many sequential operations, errors can quickly build up to the point where we can't trust the results anymore. This is what we mean by building a fault-tolerant system. It means that all of the computation steps, when cascaded together, have to prevent errors from growing. So we get an accurate final answer at the end. So how do we prevent the effects of noise on quantum computers? There are three strategies that we're pursuing. The first is to try to filter down the noise as much as possible so that we are reducing the amount of noise that can impact the system. We do this using some of the infrastructure that I showed you before, for example, by cooling systems and keeping devices at very low temperatures. We can also use different ways to shield processors from electromagnetic noise. A second way is to reduce errors at the physical level by building qubits that have better protection against noise. Here we are reducing how susceptible qubits are to the noise, for example, by using better materials or designing qubit circuits in a way that they are much more resilient against certain types of noise. And a third way is quantum error correction. Here the focus is to be able to operate robustly even in the presence of errors by detecting errors and then correcting them. These approaches are not mutually exclusive, and to get to a fault-tolerant computer, we are pursuing them in parallel to get as much reduction in error rates as possible. I will now hand it off to Fernando to dive more into how we're implementing error correction in AWS hardware.
Thank you, Nadia. I want to talk a little bit more about error correction, which is this key aspect of building useful quantum computers that Nadia just explained. And the idea is that we want to protect computation from errors, not by improving the components, the building blocks of the computer, but by using redundancy. And as I will explain, that's a key idea in quantum computation, but it's actually not an idea from quantum computation. So we use error correction a lot in current technology. We use error correction, classical error correction for bits whenever we store something in a hard drive or whenever we send some information through optical fiber. And it's I want to explain this concept of error correction by an example. And the example is what we call the repetition codes. That's the simplest classical error correcting codes. The idea is that we want to store a bit, either 0 or 1, in the memory, for example. But instead of storing just the 0 or the 1, we repeat many times the bit. So in this example, instead of storing 1 0, we store 5 zeros. Instead of storing 1 1s, we store 5 1s. And this combination of these 5 bits, like these 5 zeros or these 5 1s, we call this a logical bit now. So because logically you only have 1 bit of information, but physically you're encoding in 5 different bits. Why? Because then you can protect this from errors, right? So if you just have 1 copy of your bits in the memory, if 0 becomes a 1 or 1 becomes a 0 because of some noise process, you lose your information completely. But if you have 5 copies of it, if 1 or even 2 flip, you can still recover just by checking the majority of the bits. So you see that 1 logical bit can be constructed from 5 physical bits in this example, and we can correct up to 2-bit flips here, right? Because we can do the majority still be the right one, and we can correct back. So if you assume, for example, that noise happens independently in each one of these physical bits, which is a reasonable assumption, you see that you start getting this savings. Like now, instead of the probability of logical error is the cubic power of the probability of physical error, and if you increase your code, it reduces more and more, and then very very quickly, right, you get to store the information in a quite reliable way. So that's the idea of error correction. Is kind of simple. Let me actually explain this repetition code in a slightly different way, because that's going to be useful once you talk about the quantum case. So suppose we put these 5 bits that we have, we call them data bits, and they are this D1, D2, D3, D4, D5 in the picture here. But now we add some extra bits, and this we call ancilla bits. This will be this A12, A23, A34, A45. We didn't have to add them in to explain the repetition code as I just did, but it's good to have in this form once we go to quantum mechanics. And then we can think about performing error correction, checking if there was an error in one of these data bits and correcting back to the right, as computing these easy functions on the A12 and so on bits. For example, for A12, we would just compute the parity of the nearby data bits. So the parity of Z1 plus Z2. So we compute Z1 plus Z2 mod 2. It's just the parity. And if the parity is even, then we are fine. If the parity is odd, we know that there was an error either in Z1 and Z2. And then we do the same thing for 8 to 3 and 8 to 3, 4 and 8 4, 5. And with these parities, we can recover back the information that we had there, the logical information. And that's another way of thinking about the repetition codes. But let's go to quantum mechanics now, right? Which is the topic of this talk. So is it possible to do the same? Is it possible to correct, right, errors using error correction in the quantum case? So qubits, as we learned from Nadia, they are more complicated, right? So there are two types of errors on a qubit. It's not just bit flips that I mentioned before. There's definitely bit flips, right? So think about the qubits again as a superposition of 0 and 1. 0 can become a 1 and 1 can become a 0. This can happen in quantum mechanics. It's called bit flip error. But there is another kind of error that only exists in quantum mechanics that we also have to correct, which is that there is no bit flip, but actually in the superposition, instead of having a sum of the two components, it becomes like a subtraction, a minus sign. So a plus sign becomes a minus sign. This is what we call a phase error, and this is a phase flip error. It turns out that actually if you can correct these two types of error, you can correct any other type of error you could think of. So it's more complicated, but right, it's more complicated by this extra existence of phase flips. But then you can think, well, repetition code will not work here, for example, right? So can you find any other way of correcting this information? And another challenge is that we cannot measure data qubits directly, right? Otherwise, as Nadia was explaining, we will collapse the states and we will lose the information that is in there. So we have to find a way to learn about errors and correct them in an indirect way. And for some time in the beginning of the development of quantum computing, people were skeptical if this could be done. But around like more than 25 years ago, actually people start realizing theoretically that this could be done. And one of the best ways that we have of doing quantum error correction is using kind of a quantum generalization of the repetition codes that we call surface codes. So now I want to go to the quantum case and explain how quantum error correction works. And so this is one of the best codes that we have for doing quantum error correction. It's called surface codes. And a way to understand it is that it's the quantum generalization of the repetition codes that I explained to you in the previous slides. So think about the first row of this lattice that I have here. The first row will be basically that picture that I show you for the repetition code. So we have data qubits. They are these white dots. We also have ancilla qubits. They are these black dots. And then we do operations between ancilla and data qubits to measure parities of the data qubits. They are stored in the ancilla qubits that then we can measure and see if there was an error or not. But now, because we have two types of errors in the quantum case, we have to have two types of parity measurements here. We have the original ones that we had before that I explained to you, but now it's between groups of 4 qubits instead of 2 as the repetition code. This will be these green drawings here. But we also have to measure the parity in a rotated basis to try to detect these phase errors that I mentioned. And this will be these yellow drawings that I have here. So the price you pay now is that instead of having a line of bits, as in the repetition code, now you have a square of qubits. So there's this extra overhead that is required in the quantum case because you have to correct these two types of errors. So we have an empirical formula for how the probability of the logical qubit scales as a function of the probabilities of each of the physical components in this error correcting code. For example, the gates or the preparations, the measurements, and so on. And it roughly scale as this, as like 0.1, and then we have 100 times this physical probabilities of error to the power of d plus 1 over 2, where d is this distance of the code. In this example that I give here on the right, distance is 5. So you see that if the physical probabilities of error of all components is smaller than 1%, then there is a gain, right? We start having this exponential decrease in the logical probabilities of error as a function of the distance. Whereas if this physical probability of error is bigger than 1%, quantum error correction doesn't work. So this is what we call a threshold, and I'll talk a little bit about it in the next slides. how many qubits we need per logical qubit here, you can count, and it's 2 times d squared minus d. So now if you look at some particular examples here of this equation, right? So suppose the probability of physical errors is like 0.5%, which is roughly where we are today in the hardware as a field. In quantum computing, is roughly that's what people can do today. Then you see that it kind of already works, right? But it's very, very slow, the decrease, right? And even if you just want to have like a probability of error a little bit better than 1 in 1,000, you need distance 15, right? Which gives a very high number of qubits. It gives like roughly, it gives 435 qubits. If your probability of physical error, on the other hand, is like 0.1%, you see that you have a much better scaling, right? The errors drops much quicker. So it's important, even though error correction is probably going to be needed to get to this level of 10 to the minus 9 or less performance that we think we need to get to useful applications. It's also important to get really good physical components, because otherwise the drop in logical probabilities of error is just too slow. So let me talk a little bit more about this quantum error correction overhead that I mentioned. So this is a plot where we on the y direction we have the physical error rate, and on the x direction we have the qubit overhead. As I mentioned, there is an interesting number which for the surface code example is like 1% or around 1%, which we call error correction threshold. This is a threshold because if our physical components have error bigger than this threshold, error correction cannot be done. And therefore there is no systematic way of reducing errors further. If you're below it, then it works, but you have to be a bit careful, because if you're very close to the threshold, then it works in principle, but it's very inefficient, and therefore in practice you cannot do that, right? So what you want to do in quantum error correction is to be substantially below thresholds, and then you can start getting a faster drop-off and a more reasonable overhead. So this is like a plot, if you are 10 to the minus 3, as I showed you before, if you want to have a target logical error rate of 10 to the minus 10, like 10, 1 in 10 billions. So like you can apply 10 billion gates or 10 billion operations before having an error. Then if your physical components have an error 1 every 1,000 times, you would still need between many hundreds to 1,000 physical components per logical qubit, which is kind of daunting, right? So of course you can improve more to 10 to the minus 4, and this gets better. So there's this trade-off that we have to play and try to optimize over. So for example, if you want to factor a 2048 digit number, which will be enough to break RSA, we can look at the best quantum algorithm that we have, Shor's algorithm, which requires 6,000 logical qubits and 10 to the minus 12 error rates. If you put into the surface code analysis that I show you, this requires 20 million qubits at 10 to the minus 3 physical error rates. So right, it's a bit hard to build the system. Even if you want something that might be easier than factoring, maybe an early application of quantum computation is in simulation. There is an interesting model called Hubbard model that many people care about. For example, if you want to simulate an instance of the Hubbard model with 64 sites and on an 8x8 lattice, we need only 128 logical qubits, which is good, right? But it's still like 10 to the minus 10 error rate, which is challenging. And if you translate using the error correction, this translates into 320,000 qubits at 10 to the minus 3 error rates. So better than 20 million, but it's still, right, it's, there is a substantially overhead from error correction. And of course, the first is application in cryptography, and the second is application in material science of quantum computing. We could look at others, but the overhead is always significant. So this leads to the question whether there is something better that we can do than just using the surface code, right? And one lesson that we already learned from the surface code is that the better the physical qubits and the better the gates, the lower the error correction overhead. But how about if we even go beyond qubits, right, for more efficient error correction? And there are many different directions that the community is exploring here, but one that I want to focus on is what if we actually use what we call cat qubits, where we encode in this harmonic oscillator system that we can have in quantum mechanics. So to explain this, I want to go back to this LC circuit that Nadia introduced, the electrical oscillator. And as Nadia was saying, we can build this electrical oscillator and on a chip, and we can make everything here superconducting, such that there is no resistance, and we can cool it down to like a Kelvin temperature, 10 millikelvin, 15 millikelvin, for example. And if you do so, what you see is that the current here behaves in a quantum mechanical way. So the values of the current will be quantized. You can only have some discrete values of this current. And for example, if you have no current, this can be this one state. If there is one quantum of current, this can be 1. If there is 2 quantum of current, this can be 2, and so on. And we end up in equally spaced energy levels of a quantum system that we call harmonic oscillator. So instead, unlike a qubit, you have all these levels there. There's actually infinite many levels here. Of course, in practice, there is not infinite many levels because you need infinite energy to assess them. But there's a lot of levels that you can play with. And starting from work like from 20 years ago, there is some particular types of states that you can define here, of quantum states you can define here, which are interesting for us. And I will show it's interesting for error correction. And these are called these ket states. So here's a drawing of them. So first we can start with what is called a coherent state. It will be this alpha state here. And a coherent state is just a very like classical looking state of all these energy levels. So it has a very well-defined amplitudes here. And it's a state that will involve many of these levels. I don't want to give you the expression, but you can just think as a quantum state that will represent a very classical state of this object. So you can think of this harmonic oscillator, right, as in terms of electromagnetism, this would be a pretty classical state of these electromagnetic modes here. And this we denote by 0. This alpha has a fixed amplitude alpha, but we can change the phase of this guy and like minus alpha, and this is still a pretty classical looking state. This is called 1. But because they are pretty classical looking, and for alpha sufficiently big, these amplitudes, they are very orthogonal as well, and they are really like distinct objects, right? It's almost like going back to this thought experiment of Schrödinger, where Schrödinger saw, oh, what if you have a superposition of a cat alive and dead? How quantum mechanics explains this, right? And how it explains is that a cat is a very classical object, right? So when you get to that scale, quantum mechanics is not working anymore because the environment is already destroying all the quantum features you have there. So here is kind of, we don't really have a cat, but we have a pretty large quantum object, right, in 2 distinct states, alpha and minus alpha. But here, right, because it's not a real cat, it can still be in the lab, you can put them in superposition. So you can have superposition of alpha and minus alpha, and you can have a different phase as well. And this is called like this even cat on the left here, and the odd cats, right? So, and this is what we call a phase space picture of it. So we have like now a phase space set of all these levels. We have like a plane, and a 0 state will be a cat on the right, a 1 state will be a cat on the left, and once you put them in superposition, you get these like funky pictures that you can see here. So how you actually build this cat, right? So you need to build this harmonic oscillator, and we want a microwave oscillator because then it's in the same frequency as the superconducting qubits that Nadia explained, and then we can actually control and manipulate this cat states, right? Because as Nadia was explaining, a harmonic oscillator, all these levels are equally spaced, so there is no direct way of actually controlling the information there. But with a superconducting qubit, we can do that. So we built a microwave oscillator. It's like a coplanar oscillator that we built in the lab on our AWS Center for Quantum Computing. Here's a picture, and we are exploring how to build this cats there. But why I'm mentioning these cats? Well, because we believe they are promising in trying to reduce this overhead in error correction that I explained before. So as I was saying, there are 2 types of errors to correct in the quantum case, and we can correct each by a different strategy. So what we want to do is we want to make the cat qubit very robust to one type of error, bit flips, at the hardware level directly without any extra encoding. So this can be done. Bit flips errors can become very unlikely if we add what we call engineered dissipation that always loses pairs of photons to the environment. So this is a drawing to understand what's going on. So we have an oscillator, would be this like black picture here. But now we engineer using superconducting qubits or superconducting qubit type element, a coupling with some other resonator that we call B, such that two photons of this resonator A get exchanged by one photon of the resonator B. But now we make the resonator B by design very lossy, so it loses a lot of like photons to the environment all the time. So the effect you see here is that two photons from A get very quickly mapped to B, to one photon of B, and this photon of B leaks. So now we have an environment, effective environment for A that loses pairs of photons. But what you can see is that these cats actually like this kind of dissipation, so they are stabilized by this kind of dissipation. And then once we have this dissipation, we have something that is called bias noise. So bit flip errors, they become much less likely than phase flip errors. So this stabilization really makes very hard to go from one cat to the other cat state. There's like a big barrier between them. And this barrier scales really exponentially with alpha square. And alpha square is roughly the mean number of photons that you have in the cat states. So you see that when you increase alpha, bit flips becomes more and more unlikely, and you pay a little bit of price of phase flip, but it's a very mild price. So why one can potentially use this idea of biasing the noise? We can start then actually going back to the surface code that I showed you before, and then say, well, maybe we don't need actually this plane anymore, right? So maybe now we can start going back to the line, which can give some substantial reduction in overheads. So when bit flips are equal to phase flips, we have this plot on the left, and that's just the square that I explained to you, right? But imagine now the bit flips are somehow smaller than phase flips. Then actually the direction, which is like the y direction, which are correcting these bit flips, then actually we can make it smaller. And now we have what we call like a strip surface code, right? Like a asymmetric surface codes that corrects more phase flip than bit flips, because bit flips are already much smaller, right? And in the limit where bit flips are much smaller than phase flips, and we kind of don't need surface code to correct them, we end up in the repetition codes, right? So now we can think that you have a repetition code for correcting phase flips, and bit flips are correct directly on the hardware level by the cat qubits. So this is what we're working on in our lab, among other things, at the AWS Center for Quantum Computing. We recently built a stabilized cat in our lab, and I want to show you some results which are exciting, that we could see this like improvement in coherence time against bit flip errors. And in this case, it was an improvement of 3,500. And we keep working on that. So that's the chip that we built on the right. So you see this resonator that I showed you before is part of it, right? Is where the cat is. But then you need all these things on the left. It's called like the HCS and the buffer and some filters. This is to engineer this two-photon dissipation process that I mentioned to you was very important. We also have a superconducting qubit here. This is a superconducting qubit called transmon. That's important for readout. And then, using all these components, we created this cat, right? So this is the cat again. 0 is this plus alpha coherent state. 1 is this minus alpha coherent state. And we do an experiment where we prepare initially at time t1, at time 0, the alpha state, right? Which is just here on the right-hand side of phase space. And then we start measuring, where is the cat at time t2 and time t3 and so on. And then we see at some point, there is a bit flip. It goes to the other side, right? So you can see here in the picture, times t3 is already like some good probabilities of having flipped. And we see that now the time scale for having a bit flip in this experiment is 5 milliseconds. But where did we start with, right? So without like this, hardware efficient error correction layer, our lifetime, right? So the coherence of our initial qubits was very, very small, around like 2 microseconds. So now you see, right, or even it's like 1.5 microseconds. So now you see this like around 3,500 fourfold improvements in the coherence due to having these cats and this two-photon dissipation. So that's exciting, right? So it's great to see this, and this is just this exponential increase that I show you of the lifetime or of the coherence as a function of alpha square. So you see an exponential increase. This is like log scale up to this maximum value of 5 milliseconds, and then we have a decrease due to heating and other effects in the system that we are currently studying. So this is exciting, but of course this is just halfway, right? So we still have to correct phase flips, right? Or maybe we even want to correct bit flips more. So we need still this outer encoding, right? And that's the idea of how we can actually build a logical qubit with cats. So building logical qubits beyond what we call the break-even point, which is simply the point where the logical probability of error is smaller than the physical probability of error of the components, which is the bare minimum, right, for paying off building logical qubits. This hasn't been done yet in any system, and is actually, I think, a big challenge and a big milestone on the road to fault-tolerant quantum computing. As I mentioned, it's not trivial because there's this threshold, right? So we really have to improve our physical components beyond this threshold, and we are just starting to get there now. But of course, we have to do the physical components very reliably, and at the same time build a lot of them, and that's also challenging. So that hasn't been done yet, but I think that we are on the right track of doing that as a community in the next few years, I believe. And I want to advocate in this slide that this repetition cat code, which is combined this cat code just with the simple repetition code that I mentioned before, is an interesting candidate for getting beyond this break-even point and getting a logical qubit that works for the first time. So these are some simulations that we did where we look at the logical lifetime versus the repetition code distance. And they have like distance 3, 4, 5, 6, 7. And these are just some numbers that we assume both for the lifetime of the storage resonators, which is the first one here, and for the transmon, our superconducting qubit, which you also require here, which is the second. And the break-even point will be like some black line here that actually you cannot even see. And then you see that, like for all these different assumptions, right? Of course, the better the physical components, the better the performance of a logical qubit. But you see that with some numbers which are, not easy to achieve, but realistic, there are good prospects for getting this break-even. And therefore, we think this is a good direction to pursue. Now, once you get these logical qubits, that's not the end of the story, right? So actually, how you would build a fault-tolerant quantum computing with this idea of cat qubits, we actually worked out details of a scalable quantum computer with cat qubits to assess the long-term potential in a publication that we had last year. And the idea is that we'll get these cat qubits, and then we'll build like these unit cells here on the left, and these unit cells we put them together to build like these strip surface codes, which will be each one of these kind of like blue and red objects on the right. And then we have a lot of these logical qubits, right? In this case, we have like 9 logical qubits in this drawing. We need some space between the logical qubits to move the information around. And we need these things on the left and on the right, which I call magic state factories. And they are useful to implement some particular logical gates, which are harder than the general one. So they are required for, you really have a universal quantum computer, and then there's some extra space for them. And what we can find is that there is potential using cats for even like bigger than 10x overhead reduction. If we can do gates, physical gates with the cats as reliably as we can do with normal superconducting qubits. So that's promising, right? So this idea of bias with the noise, I think, can give us some leverage. And we should explore that because, as I mentioned, the overheads are so big right now, right, as we understand them. But we also found from our analysis that it's actually harder to get good gates, good physical gates with cats than with transmons, for example, or other superconducting qubits. And that's something that we are working on right now, right? So as usual, it's a trade-off, right? So there are many different and interesting directions. We think cats might be one of them, but there are still things to work out and to figure out. So then we have to work on our physical components, right? As Nadia was explaining, we have to work on the error correction, as I explained. But then there is still another challenge, which is just we know with whatever scheme we come up with, we will need to scale these quantum systems to a much bigger scale than what we can do today. We need to build a fault-tolerant quantum computer with more than like 100 logical qubits, which is what we think is required for getting interesting applications of that technology. This will require at least many thousands of physical components, probably hundreds of thousands, even millions of physical components, right? And of course, eventually, we want to be at the same stage as we are with our classical computers today. We want to have billions of physical components, right, of quantum physical components. And we think there is a viable path with superconducting qubits for that regime, but it won't be easy. So it will require really, on top of the scientific discoveries and advancements that I was explaining some of them, we also require very substantial engineering advances, both in cryogenics, also in software stack and in control. So just to give an example, right? So we have this dilution refrigerator that we use for our experiments at AWS Center for Quantum Computing. You can host maybe like 100 qubits here, something like this. Depends on what you want to do with them. But not more than that, right? So maybe 1,000 one day once they build a bigger one. But what really we require is probably to have a lot of these fridges, and we have to connect them somehow, right? So really you build a data center of these fridges, right? And then you see how to make a big quantum computation using all of them, right? So these are some challenges that are in the future, right? But we have to start thinking about them today and start to make progress on them as well, in addition to like the scientific progress that we have to do to just have better qubits and better gates and clever ways of doing quantum error correction. So now I turn it back to Nadia, and I thank you very much for listening to me.
Thanks, Fernando. So I think it's clear that we're seeing very promising results, but we're realistic that we have a long journey ahead of us. Even with a fault-tolerant quantum computer, we estimate that it will take more than 1,000 logical qubits to tackle high-value problems, like quantum chemistry and material simulations with exponential speedups. The first major milestone on this journey will be demonstrating a logical qubit. And as Fernando explained, we have to get beyond the break-even point, so the logical error rate becomes less than the physical error rate of the qubit we started with. But one logical qubit will not be enough. The next challenge will be to perform gate operations between logical qubits while maintaining accuracy. This is really hard because it requires getting blocks of physical qubits to interact together, so it will require additional control in order to maintain low error rates. At 100 to 1,000 logical qubits, we think quantum computers will already be able to demonstrate some speedups for more targeted problems. But we want to scale even beyond that to solve real-world problems for customers. And that will require even further scaling, including advances in engineering systems to support and control quantum devices. In parallel, we'll also keep working to improve physical performance of quantum hardware and increase the quality of qubits and improve accuracy of quantum devices. And of course, another very important area is to continue to identify the best way to use quantum computers. So we'll continue to work on algorithm development and look for interesting problems for us and for our customers to benefit from quantum approaches. Even though building a fault-tolerant quantum computer is a long-term effort for us, there are opportunities to engage with us today. So I'm going to mention a couple things you can already do. One thing you can try is Amazon Braket, our AWS service for quantum computing. This lets you access quantum processors via the cloud and gives you the ability to try different types of quantum computers, all from one interface. AWS has partnered with several hardware providers to make their devices available on Braket, including D-Wave, IonQ, and Rigetti. You can also use several quantum simulators to test quantum circuits on classical hardware. Another option, if you're interested in quantum but are looking for more hands-on guidance, is the Quantum Solutions Lab. This is a great option for customers looking to become quantum ready. This team of experts works closely with you to identify near-term solutions for your business, and they can also help you optimize current approaches by building classical and quantum-inspired solutions that take advantage of machine learning and high-performance computing. I hope that you're as excited as we are about the future of quantum, and I'm glad that Fernando and I had this chance to tell you about our efforts at the AWS Center for Quantum Computing. We look forward to working with you as we continue to make progress on this journey.